the diene. Yes, this is the diene. That is, first do the asterisk to each carbon. This is the diene. That is, diene means two double bonds. That is double bond, single bond, double bond. But in case of benzene, there is a presence of extra double bond. So for diene, we know this is homoannular diene. For this, lambda max value is 253 nanometer for homoannular diene. But apart from these diene, there is a presence of another double bond, and which are conjugation with these two double bond. That's why this extra double bond is called as double bond extending conjugation. Don't confuse. Always see where the double bond extending conjugations are present. Very confusing term is, for this extra double bond, we have to add 13 nanometer and then calculate the lambda max value. This is very simple calculation, but we forget these all things. What is meant by double bond extending conjugation? Simple term, double bond extending conjugation. That is, this is the diene. The extra double bond, which is conjugation with these double bond, are called as double bond extending conjugation. Now, I think this is clear now. So the next, oxochromes. Oxochromes means any functional group that increases the lambda max and Emax also. It's like functional group like OR. OR is, you already know, OR is the alkoxy group. For alkoxy group, there is an increase in the 6 nanometer. For sulfur, SR group, there is an increase in the 13 nanometer. And for chlorine, bromine, there is an increasing in the 5 nanometer. For secondary amine, there is an increase in the 16 nanometer. And for this acetyl, COCH3, OCOCH3, there is an increase in the 0 nanometer. Very interesting reason for all this, but we discuss it later on because we have very less time. That's why these reasons are discussed later on. First we see how to calculate the lambda max per structure, because this is very important for any examination. That's why first we see this, then see what is the concept. For this, we have the problems. Solve this problem first. Very simple problem. I have one strategy how to calculate the Woodward-Fieser rule very simplified manner. Remember, write down this. First, identify the structure, and where double bond are present, do that asterisk. First we see the example, then we calculate how to these are calculated. Take a simple structure. This is the simple structure. Okay? First step, write down where the conjugation are present. See, the conjugation is present on this carbon. Do the star on this carbon. This carbon, this carbon, this carbon. First step is that is giving the star or mark the star on conjugated carbon where the double bond is present. That is in conjugation. Okay? Then, first see, second rule, identify is it homoannular or heteroannular. See, homo or hetero. In case of this structure, this is the conjugation present in, that is diene present in same structure. That's why this is the homoannular diene. And the basic value for the homoannular diene is the 253 nanometer. Okay. Third, See, what are the exocyclic double bond present in this? Exocyclic double bond. See both the ring. This is A ring, this is B ring. How to see the exocyclic double bond? See, what conjugation is present in this ring? So, see, is there any double bond present outside the ring? No, there is an absence of the exocyclic double bond. But there is a presence of exocyclic double bond for this ring. But there is an absence of conjugation in this ring. That's why we not calculated this for exocyclic double bond. That's why exocyclic double bond conjugation is taken as 0. Because absence of exocyclic double bond. 4. See, ring residue. This is very important. Ring residue. For each ring residue, we have to add 5 nanometer. Remember this? I think here we are ring residue are missing. So add this to this chart. Ring residue, for each ring residue, there is an increment of 5 nanometer lambda. Then, how to calculate the ring residue? There is the use of these star. How to calculate the ring residue? See, those carbon which are present in the conjugation, ring residue are present in front of this. This is one ring residue. Here are conjugation. Here are conjugation. So there is a no ring residue. Here are also conjugation. There is a no residue. But in front of this, there is a no conjugation. That's why here is the another ring residue. And in front of this, there is another ring residue. There are 3 ring residues are present in this structure. Very simple. Only understand this concept. Ring residue always present front of the carbon of conjugated. These conjugated carbon, first, second and third. Here is not ring residue because these two are in conjugation. Hence, there is no ring residue between conjugated carbon. There is always ring residue in the conjugated carbon in front of that carbon which have the non-conjugation. Simple this. There are 3 ring residue. That's why increment is 15 nanometer. Because one ring residue of 5 nanometer, 3 ring residue of 15 nanometer. Then next, 5th rule. See, is any structure contain double bond extending conjugation? We already know what is meant by double bond extending conjugation. In case of this structure, only two double bonds are present. That's why there is no chance to presence of double bond extending conjugation. There is a chances of double bond extending conjugation present only when there is an extra double bond present apart from this diene. So there is only 2 bonds present in structure. Hence there is an absence of double bond extending conjugation. Thereby taken as 0, 0 because there is absence of double bond. Last, see what are the increments. Increments means any presence of alkyl group. If alkyl group is present, take 5 nanometer. If OR is present, take 6 nanometer. If any alkyl group present on structure. Suppose example, the methyl group is present on this structure. Then there should be for alkyl group there is an increment of 5 nanometer. If presence of this methyl on this carbon, that is conjugated carbon, always remember the increment always taken only when there is a substituent present on conjugated carbon. That's why I am first time star both conjugated carbon. If CH3 is present on this carbon, then there is no increment because this carbon is not present in the conjugation. Only ring residue consider for those carbon which are conjugation with each other. This is the simplest way. And here in this structure, there is a absence of any ring residue. So that's why it is taken as 0, 0. And then finally calculate the value. And our final structure, that is final value, 253 plus 15 is equal to 0.268 nanometer. This is your final answer. And this is question of this year 2015. Recent, these days. Morning, one of my junior used this question, that is, he will tell me, actually he was telling me this is the structure in NIPA exams. That's why I has taken Woodward Fieser rule, how to calculate. Because many number of times students are very confusing how to calculate the Woodward Fieser rule. For easiness, remember these 5 rules. First, give the star to the each conjugated carbon. Second one is the identify. Structure is homo or heteroannular dyne. Third one is the identify the which exocyclic double bond present. Identify the ring residue. Ring residue, how many ring residue present on the ring. And last one, fifth one is the double bond extending conjugation is present on ring or not. And last, what are the increment that only present on conjugated carbon, not increment calculated if they are present apart from conjugated carbon. This is the 6th main rule. Please write down these all rules. Then we have solved many examples. Now let us start with another example. Simple example. You have to solve and practice. This is the structure, and something missing in previous structure. That previous structure contains these, and they are considered these also exocyclic double bond for this ring. That's why they are adding 5 nanometer in the structure. Sorry for that mistake. They are also calculate the ring exocyclic double bond for this ring also. So sorry for this mistake. Add this 5 nanometer to the previous one. Now draw these structures. Calculate the λmax for this structure. We have 6 rules how to calculate the λmax for this structure. First, assign the carbon which are in the conjugation. That is, these, double bond, single bond, double bond. These 4 carbons are in conjugation. Second rule, identify homoannular or heteroannular. Is it homo or hetero? Yes, obviously it is heteroannular dyne, because if the conjugation is present in between 2 different rings. That's why basic value is the for heteroannular dyne 250 nanometer. And third one is the identify the exocyclic double bond. See how to say exocyclic double bond. See this ring. Is there exocyclic double bond present? No. See this ring. There is exocyclic double bond present? No. That's why exocyclic, there is an absence of the exocyclic double bond for these structures. Third one is our ring residue. Which are the ring residue? Always say ring residue only do on those carbon which are in the conjugation. First see this carbon. Do ring residue on in front of this carbon, in front of this carbon, in front of this carbon, in front of this carbon. There are 4 ring residue. That's why increment is 20 nanometer. Fourth rule, is there increment present? No. There is a not increment present because there is a no substitution on any carbon. That's why increment is also not present. And see, next rule, That is there presence of double bond extending conjugation? Here is only 2 bonds, so there is no question of the double bond extending conjugation. Yes, and last rule, is there presence of any oxochrome in this structure? Means any functional group? No, because these conjugated 4 carbonyl, no any other another substituent are present in this carbon. That's why the final calculation is the basic value and our ring residue. That is total is 235 nanometer. This is our final answer. Yes, this is correct. These type of questions mainly asked in exams for the very competitive exams like NIPL, GPAT or any drug inspector exams. Calculate. This is our similar one. Calculate for one of hard example. Calculate. This is very important to calculate the λmax for very complex structure. We are now in the master. We also have the Woodward Fieser rule for 10 or 15 marks for our theoretical exams. That's why it is very important till our completion of all pharmacy syllabus. So that's why Woodward is very important for our pharmacy careers. Calculate the Woodward Fieser for this very complex structure. Don't fear, this is very big structure but not difficult if you solve by assigning various rules of our Woodward Fieser rule. Our first rule, assigning the star to those carbons which are in the conjugation. See this, double bond, single bond, double bond, single bond, double bond. These 6 carbons are conjugation with each other. Do the star to that carbon. Okay, our first step is completed. Second step, identify is it homoannular or heteroannular. This is very interesting structure because these contain both homoannular and heteroannular. How? See, these double bond, single bond and double bond. These are heteroannular, okay? And these double bond, single bond and double bond. These are homoannular diene. Write down this rule. If a structure contains both homo and heteroannular diene, that time take parent value as a homoannular diene, because homoannular diene have higher λmax. That's why we always take parent as a homoannular diene. That's why our basic value is 253 nanometer. Simplify these examples because remember these rules. When structure contains both the hetero and homo, that time select the homoannular diene because it has the higher λmax. Simple. Next, our rule is the presence of any exocyclic double bond to the ring. See this exocyclic double bond. First, see for this ring. There is presence of one exocyclic double bond for A ring. One exocyclic. See for B ring. For B ring, there is absence of exocyclic double bond. C for C ring. See this, but this is not a actual exocyclic double bond. This is not an exocyclic for this C ring. When it is exocyclic, if the double bond is present on this side. Hence, in our structure contains mainly 2 exocyclic double bond. When it considering about this is 1 and this is about 2. That is the structure 2 exocyclic double bond or 1 exocyclic. See this ring, C ring. this double bond, these are exocyclic to the same ring, that is one exocyclic double bond, and this ring also contain another exocyclic bond. That's why there is a presence of two exocyclic double bond. In case of this ring, there is nothing present of the exocyclic double bond. That's why structure contain two exocyclic double bond. And next our rule is the ring residue. How to draw? How to calculate the ring residue? See this. There are 6 carbon which are in the conjugation. First, see, ring residue done on only those carbon which have in the conjugation. First, see, ring residue on this carbon. Second, on this carbon. Third, on this carbon. There's on 4. 1, 2, 3, 4. Yes, there are 4 ring residue present in our structure. That is 20 nanometer. Fifth rule, that is any increment present in our structure, any alkyl group or any functional group. If you see structure, there is an absence of any increment in the structure. There is nothing about the increments. And last one is there presence of any double bond extending conjugation? Yes, because if we consider our structure content parent is the homoangular line, okay, these and these are line, but another double bond which are conjugation with these ring, series, single bond, double bond, and this extra bond is called a double bond extending conjugation. The basic value is 30 nanometer. And calculate for all these 30, 50, 60 and 53. Around 330 nanometer. This is our final answer. See, yes, 330 nanometer is our final answer. Okay, this is all about dyne. I think this is clear now how to calculate dyne. Most of time, dynes are asked in the rest of the exam, but we are also seeing what is the conjugation for how to calculate λmax for alpha beta unsaturated ring system.